Good afternoon, everyone. And I firstly want to thank you all for joining our webinar today and getting connected with us and having this webinar with us. That's a pleasure to have you and getting connected with you. So for today's webinar, we will be basically having an overview of geothermal energy, and also we will be presenting our nGEL project that which we are conducting at the moment, which is next generation flexible trigenerational geothermal ORC power plant. So for today, that's basically the topic that we are going to be having the webinar about. And I will be basically hosting the meeting and will give the first part of the presentation about the project. I'm basically Shahin Jamali to give an introduction about myself, and I'm basically working at Fraunhofer IEG. I'm head of a monitoring and AI competence center. And on the right side, we have our technical manager of the nGEL project, Mr. Turul Hazar, and he is basically the R&D assistant manager of Zolu Energy, which he will be presenting you the second part of the webinar. So just to start and give an introduction about the nGEL project. So nGEL stands for Next Generation Flexible Trigenerational Geothermal ORC Plant, and that is what it is standing for. I would like to start with an overview of the project, so giving you a little bit brief facts about the project. So the nGEL project is part of the Horizon Euro Framework Program, and it's part of the Research and Innovation Actions with roughly an estimate of 5 million euros in budget. In total, the project will be running for 4 years, 48 months. That would be the duration of the project. Throughout the project, we are trying to achieve 3 key technologies and develop them while having 6 milestones to achieve throughout the lifetime of the project. And these milestones will be basically achieved throughout good, excellent 7 partners that we have that you can see on the right side of the screen. The partners are Fraunhofer, which is coordinating the project, and then the other project partners are Technovative Solutions, Zolu Energy, Geolone Island, Fito, REPG, and NonDeo. So that's basically what the consortium members are and project consortium is consisting of. I would like to talk a little bit about the mission of the project. So as you see on the middle of the screen, I want to talk firstly about the energy demand focus. So heating and cooling, not considering the electricity, accounts for 46% of EU energy consumption, which is a very significant amount. But when you consider the part that the renewables play, it's only 18%, which is basically not that much. So within the nGEL project, we target to basically go for these untapped potential of low to medium temperature geothermal resources to basically balance energy demands. And that will basically translate to our core mission, which you can see on the left side of the screen. And our core mission, based on the energy demand focus, is to transform geothermal organic Rankine cycle, the ORC power plants, into flexible tri-generation systems. And what do I mean by tri-generation is to produce electricity, heating, and cooling, and basically supporting that and having the backbone of AI and data-driven integrated energy management systems. So that's part of the innovation that we have. And bringing these two together, we aim to have the mission of having a scalability potential to make these technologies scalable across the EU. So hypothetically and theoretically, if the nGEL technology can be successfully implemented, it can basically meet 4% of the EU's current annual heat demand. And considering the natural gas imports and prices, it would be an equivalent of around about 9.6 billion annually in economic savings. So that's basically more or less, in a nutshell, our mission within the nGEL project. But every mission has its own challenges. So we have identified 4 main challenges in achieving these goals. And the first one is the energy consumption gas. So as I previously mentioned, 40%, 46% actually of EU's energy use is heating and cooling, but renewables only cover a fraction of this demand, and it's around 18%, which is basically not that much. So this is one of the main challenges within the sector right now. The second one is within Europe, we have a lot of reliance on fossil fuels, basically natural gas, and that's the primary source. And as you know, it creates an economic and environmental vulnerability for the continent. The third one is that if you're trying to use renewables, mainly at the moment, solar and wind, these are intermittent energy sources. What does it mean? It brings grid instability and challenges in grid stability. This is one of the main challenges also at the moment. And Europe has abundant low enthalpy geothermal fields, but they are underutilized. And especially when we are talking about ORC plants, this is not utilized that much. So these are the challenges currently that we have in Europe. And in order to overcome these challenges, there are some requirements. So what do we need? Basically, the first one is that we need a flexible and scalable renewable energy to basically overcome these challenges. Within nGEL, we are trying to overcome that with a tri-generation system to provide flexibility and also meet the demand of various energy demands that happens at the same time. How do we do that? We also integrate real-time demand response. When I was talking before, this is basically with the backbone of AI-driven energy management system. We integrate that with cold and thermal energy storage solutions, novel ones, and with that, we enhance this grid compatibility and also supports the day-ahead energy market. So we consider the day-ahead energy market, and we bring real-time demand responses to the grid to also have the challenge of grid instability solved. And the next one would be scalability across the EU. And within our technology, we aim to target sedimentary formations also. And this basically will translate into being able to implement it widely with new and also existing ORC infrastructures. So that's basically the challenges and what we need to do. How do we do that? And that basically is the project objectives. The main one, I don't want to be redundant, is to design flexible geothermal ORC plant that has tri-generational capabilities. That's heating, cooling, and electricity production, while we ensure environmental sustainability. There are cores and pillars to do that. The first one is to design and develop cold thermal energy storages and heat or hot thermal energy storages. So these are the main two ones. We want to integrate, and we are aiming to integrate AI-driven and data-driven digital twin of the ORC geothermal power plants, and then further improve that by integrating an energy management system for these flexible scenarios and situations for the power plants. By doing so, we will increase the reliability of the ORC against high ambient temperatures because this AI-driven digital twin compensates for that and considers all these aspects. And then bringing all these together, we will have a demand-side management control strategy, which would be controlling the power plant to optimally do the tri-generation capabilities. So moving forward, I want to bring it as a whole into three main points of what we are trying to do. The first one would be the AI-driven EMS. That's basically an AI-based energy management solution that would schedule power, electricity, heat, and cooling output in real time. And what does it consider? It considers the market demand and the forecasts and all the historical data that is available with the consideration of the power plant production. The second one, how to achieve that, would be basically utilizing cold thermal energy storage and also hot thermal energy storage solutions. And these storage solutions basically ensure energy availability during peak demands for heating and cooling, and that would compensate and bring stability to the grid. And the third one would be the usage of absorption chiller and heat exchangers to basically be able to support the cold and hot thermal energy storage solutions, and it would enhance multifunctional usage of those technologies. We will have, as an outcome, multiple innovations, and the key innovations would be, we would be developing a digital twin of ORC plants, and this AI-driven digital twin would be able to be used for our care and demonstration cases, which I will be talking about, and our technology manager also will be talking about that. But that would be basically the first and one of the main innovations that we would have. The second one, which would be a complementary technology to that, that would be the demand side management, or the DSM, which would be able to implement adaptive control strategies to handle fluctuations when they occur in the demand and grid needs. And by doing so, one of the main innovations would be enhanced resilience. What does it mean? It means that we ensure operational reliability with the AI-driven models, and also the historical data and the data that we have from the ORC power plant, to even function in high ambient temperatures, which would be essential for summer demand spikes. And then we complement that and bring the enhanced resilience using our storage solutions. And all in all, it would be done through a smart control integration, which optimizes this flexibility of tri-generation output through between power, heating, and cooling. So that's all in all our main and key innovations that we are aiming to achieve within the project. And these will be done through three main methodologies: developing of the digital twin, the heat storages, the thermal storage units, the cold and thermal one, the hot one, and the demand side management. And all in all, we are doing all these three through a design philosophy that basically summarizes into having flexibility, environmental sustainability at its core, while being able to scale it later on for various European regions. So that's how we are trying to design the technology. That's our design philosophy. The first and foremost pilot region. So we want to demonstrate the technology in a field scale, in a large scale. And basically, we have selected a geothermal power plant in the Kizdeler village in southwestern Turkey near Denizli. So Toro will be discussing a lot about that, but that's the target pilot region that we have. The goal there is to basically demonstrate all these technologies, test the scalability, optimize the EMS that is developed, and also evaluate the environmental and also economic impact of the nGEL technology. And we would be doing community engagement. We will be basically partnering with local energy providers to adapt the solutions to what is the needs regionally, and also based on the infrastructure that is available over there. So at this point of the presentation, I would stop and I would give the floor to Mr. Tuyrul Hazar, our
I'm hoping I can get the
technical
control
manager
full
of the
screen.
project. Let me try to give you control.
While
Okay.
he does that, hello everyone, and welcome again. Thank you, Shine. Welcome again to our webinar regarding our project called nGEL, which again stands for Next Generation Flexible Tri-Generation Geothermal RC Plant. My name is Turul Hazar, as Shine already introduced me, and I act as Assistant Manager in R&D department in Zorlu Energy. Thank you for your interest in our project, and I hope this will be informative and fruitful event for everyone joining in. Well, before we go into in-depth details about our project, which especially focuses on the ORC geothermal power plants, let me briefly explain what the geothermal energy is, or what kind of power plants there are, and of course also what are the advantages and disadvantages that makes investors decide which type of power plant would be installed depending on the local conditions. I believe this will be better to help you understand the purpose of the project better and in more clear perspective. And as Shaheen, I believe, already have given some information about the methodology and philosophy, I'll go into more about the engineering part of the project. I'm not sure why not, but I can't seem to move the... Yes, that's great. So, what is geothermal energy? As you know, the geothermal energy is the heat of the world, our Earth itself. It's the core of the Earth that has a lot of heat inside. When billions of years ago the Earth was formed, thanks to planets' collision and sacrifice, there was immense heat which its residues still is trapped inside the core. Additionally, decay of uranium, thorium, and some other elements release a lot of heat. There are some other causes as well, but these are the main source of heat, and I don't want to go into more details about the geological formations. This heat inside the core is transferred from the core of the planet to the crust, where we, humans, tap into this heat and use it for many purposes, namely, and have used it for thousands of years. namely hot springs, tourism, health, and the last couple of centuries, we've been starting to use it for power generation and a more digital and efficient heating district purposes. So let's move on to the next slide. Great. So as much as I'd love to talk more about the health benefits of the geothermal, I would not want to divert the focus from the important subject we have at our hands, which is the power generation from the geothermal heat. Geothermal power plants, or as we call it, GPPs in short, use the heat that moves up into the crust from the geothermal reservoir. And this especially is more dense in areas where the tectonic activity is high and there are many more fault lines than the other areas. Fault lines help transfer the heat, acting as a highway by means of fluids such as steam, gas, and water, or sometimes a mixture of all of them together. The power plant type depends on the reservoir characteristic, of course, and there are some other parameters as well that you need to consider. The main parameters that affect the design are the temperature, pressure, and the fluid type. And of course, there are some economical factors as well. There's a small delay on this presentation, so sorry about that, but I'll try to keep up. So generally, the power plant type depends on the temperature and enthalpy of the geothermal fluid. However, only high temperature, as the table suggests on the below, would not be enough to decide if the plant is going to be flash or dry steam or sometimes binary type of geothermal power plant. If the temperature is high, but the mass flow is relatively low, that might suggest an ORC type plant. If the fluid type is water or steam mixture, the flash cycle will be required for maximized efficiency. Or sometimes you can use both plants in combined section, such as having a flash cycle and then having a binary cycle at the end of the flash cycle, which would make a combined cycle. Economical factors such as internal return rate, capital expenditure, and so on, of course, would also play a big role on this decision. Lastly, the chemical composition of the geothermal brine is quite crucial. You require a clean geothermal brine to utilize a flash cycle. Otherwise, your temperature on the reinjection side drops when you utilize the geothermal brine. And when the temperature of the geothermal brine drops, that means the solubility of the minerals inside the geothermal brine that depends on the area and the reservoir will decrease. And there's going to be some sediments on the flow that might block or drain, stop some blockages or stop the drainages in your piping system, which would require a lot of operational expenditures that is quite unwanted. In that case, you might want to opt for the ORC power plants as well. So moving on to the next slide to explain more in detail about the geothermal power plant types. So what you can see on the screen is a dry steam power plant. Thanks for the illustrations from the Say One Energy. And in dry steam power plant type, the pressure and the temperature in the reservoir is in such condition that when the fluid comes up from the production well, it flashes into steam 100%. Only demisting is required for this system. The demisting is only done to remove the suspending liquids in the steam, so it cannot cause any damage to the turbine blades. So only after the demisting, the flash steam, the steam itself, enters the turbine, and after the turbine, it's of course after the power is generated through the generator connected to the turbine shaft, the steam is then condensed into liquid, and the only purpose of the condensing the process is to be able to re-inject the fluid into the reservoir, so the sustainability is still there and you can utilize the same fluid after it reaches a certain temperature inside the reservoir again. So if we move on to the next slide, which is the flash steam. In flash steam power plants, the fluid comes up from the reservoir, again, similar to the dry steam, but in three phases. These phases are being steam, liquid, and gases. In geothermal sector, we call them non-condensable gases, as we cannot condense them down. They require high, immense pressures and temperatures, or low temperatures to condense. So usually they are released into the atmosphere. But that's a complete another issue that we might talk about in another webinar. While there is steam in the flow, by dropping the pressure in the equipment that's called separators, or sometimes we call them flash tanks, more steam is generated, so we can generate some more power. And this steam is, of course, then directed to the turbine, as you can see in the illustration as well. This is sometimes done in a cascading configuration. Then you can have high, intermediate, or low pressure steams that enter the turbine in different locations to generate more steam. Same process with the dry steam power plant applies here. After the turbine, the steam is then condensed and reinjected along with the unused brine from the separators. So moving on to the last type I'm going to talk about today is the binary cycle. In binary cycle type power plants, the fluid temperature or mass flow is not enough to opt for the other options. So you cannot flash it, or you cannot create steam directly from it, or you could, but it would not make sense financially, which requires an organic fluid with parameters such as evaporation temperature and enthalpy values that are within the desired range that you can utilize for the power generation. In binary cycle process, the geothermal brine only heats up the organic fluid to create steam of the ORC, of the organic Rankine fluid, and then the brine is then reinjected. The only purpose is now achieved. The organic Rankine fluid is now used is in a similar manner as the previous plant types. It's basically a Rankine cycle that you utilize. You have steam, you generate some steam, you utilize it to generate some power from the turbine, and after the turbine, you condense it down in a condenser, and then use a pump to direct this flow again to create a continuous loop that you can generate power from. In this ORC power plants, usually the water is not really abundant, so you need to utilize an ACC, which is air-cooled condenser. Then you rely on the ambient temperature, but I will go into more details about the temperature effects on the system in oncoming slides. So let's talk about the geothermal energy in EU market. As of 2023, I will reference the 2023, by the way, because the new EGEC, European Geothermal Council report will come up by the end of, I think, May this year. So only the reference we have from is from 2023. So as of 2023, the geothermal sector in EU as well as the whole globe is steadily growing. And there is more than 140 geothermal power plants operating in EU and EU associated member states. This growth is basically driven by demand for renewable and supportive policies. Additionally, interest for heating and cooling options also increase the demand on the geothermal energy. This demand is being met by investments in various countries throughout Europe. Approximately 50 geothermal power plants are under different stages of development, and there is an increased investment from Croatia, from France, and Italy, where there's already a great amount of investments in Italy due to high reservoir temperatures and flows. While also there are some, of course, advancements in other countries such as Spain and Greece. There's currently 20 terawatt hour per year generated power from geothermal, and 7 terawatt hour of it comes from the EU member states, and the rest comes from the EU area. If you move on to the next slide, you can see, let's talk about some heat aspect of the geothermal as well. On the map on the right side, you can see on the green lines how much geothermal is used for heating and cooling, and on the blue lines how much of it is used for power generation purposes. As you can see, in the most of the EU, only purpose of the geothermal energy is for heating and cooling, which is basically, again, as Shaheen mentioned in the beginning of the presentation, due to the sedimentary formation, where you have less geothermal activity or less decreased temperatures in even deeper wells in mainland Europe, in Central Europe. Heating and cooling, of course, is mostly, again, utilized in EU, and there are 400 heating grids in EU, and 300 of them are located in the member states and not the EU area. 64 projects were announced, with developments mostly from, again, Germany, Croatia, and Netherlands. Due to political reasons, the heating and cooling become a significant topic in the recent years, especially with the conflict between Russia and Ukraine with the natural gas issues. And while considering the heating and cooling accounts for, as again Shaheen mentioned before, 46% of EU's energy consumption, the developments are only natural and will steadily grow into the future as well. As we move on to the next slide, and I want to talk about our second topic here, which is the frequency reserve. And let's talk about what's frequency and what's frequency reserve. Well, frequency is basically the changes in direction in AC, which is alternative current per second. The frequency is different in many different countries, sorry, many different regions. For example, for EU and most of the for most of the Africa and most of the Asia, the grid frequency is around 50 hertz. It is 50 hertz. But in North and South America, in some Asian countries, it's 60 hertz. This is only because it's more efficient to transfer the electricity from a place to another in a certain frequency to remove the inefficiencies, to have reduced power losses, and to have enough power density in the grid. And this is why the 50 to 60 hertz frequency is chosen for the grids. While the detailed explanation on the frequency can be found on many platforms, I won't go far into that since I do not have an engineering degree on the electricity. Standard frequency is crucial for any home appliances as well. From phone chargers to refrigerators, everything is adapted to frequency on the grid. As you can see on the presentation, on the illustration, thanks to inhabitat.com, if the demand on the grid increases without the increased supply, that means the frequency will decrease over time. And if the demand is stable, however, the supply increases on that part, which is less frequent than the initial one, then the frequency on the grid will start increasing. So if the fluctuation in the grid is higher or in longer durations, that will affect your home appliances, as I just mentioned. You may see on all electrical appliances, there is a frequency indicator, which means if the frequency goes up or down for longer durations, equipment will break down or simply do not work. In order to prevent this, transformers at home that use electrical fuses will go off and disconnect the power from the grid to the household. In a similar manner, if there's a bigger problem, transformers for smaller areas will do the same, preventing increased current flows, and damage to the products in the grid and at households as well. So moving on to the next slide. How is the frequency in the grid is then stabilized? Well, different countries use different but very similar solutions to balance the supply and demand to preserve the frequency in the grid. This is mainly achieved by running readily waiting power generating systems, may it be batteries, hydroelectric power plants, or fossil fuel generated power plants. Hydroelectric, sorry, please note that these systems work in cascade formation. You can see on the table there's a lot of information there, but I will explain briefly how they work. So they work in cascade formation. They replace each other step by step and works in hierarchy. So it starts from local to larger areas as well. So what are these? FCR, which is frequency containment reserve, is essentially the first line of defense and must be ready instantaneously without the TSO command. So this works automatically without the TSO command, but under its control. It works automatically and has the fastest response time. It has to be below 30 seconds, usually around 15 seconds, and it should go for a maximum of 15 minutes. The activation is automatic from local frequency deviation, and it usually handles 90 to 95% of the frequency deviation. So usually there is no further help required from other reserve services. So frequency containment reserve basically handles 90 to 95% of the fluctuations in the grid. But if it cannot, the AFRR comes in, which is automatic frequency reserve restoration reserve. It is used to fine-tune and control areas balance and is managed by central control systems. So it's a little different than the local control systems used in the FCR. It should respond before 5 minutes and usually is requested to provide power up to 2 hours. And if, of course, the grid requires more power to generate, or it requires more time to move on to the next stage, it can work up to 3, 4, 5, 6 hours, but is usually up to 2 hours in normal operation. Its generation is, again, automatic, but it is controlled completely by TSO. Then comes the MFRR, which is the manual frequency restoration reserve. It can be activated strategically depending on the system conditions. It is manually controlled by the TSO and prepares the system for further imbalances if it's expected. It usually lasts. It is usually the last step on the grid frequency stabilization. And the last step is the replacement reserve. It is not widely standardized yet, but it is emerging to cover longer-term flexibility needs. It is for long-term balancing across countries and regions, so this has a larger area of control. So this is a lot of information to take, so I will try to create an analogy to make it more understandable. In an analogy, just consider frequency change as if you stub your toe to a table's leg. The FCR is the reflex you have. So once you smash your leg to the leg of the smash your toe to the leg of the chair or a table, your muscle spasms or your brain just randomly takes control and stops further damage to your body. That's the initial response, which is the FCR. So the muscle spasm can be considered as the FCR, as a short duration response from the grid. AFRR would be applying bandage. So if you check your toe and there's still pain, then you try to put a bandage over it, try to handle it, and it's probably will be under control under those conditions. MFRR, on the other hand, is the doctor's intervention in this case. If the pain is persistent and you think that you might have broken something during this crash, then the manual frequency restoration reserve, which is now in analogy is doctor's intervention, comes in and checks if there's any damage and prevents any further problems that might happen. So lastly, the RR, on the other hand, is the long-term care, such as rehabilitation support. So this is for long-lasting problems that you handle, so such as the rehabilitation support you have if you have broken something in your body. So the analogy here is the initial response, usually, which is the muscle spasm, controls 90 to 95% of the problems. Same with your body. If you stub your toe to somewhere, it's usually just nothing. Maybe a small bruise will happen, but then nothing wrong will go on. And the next of the process will come in if anything else is required. I know this is a tough area to look into, and I'm hoping that this is now more clear to you guys to understand. So if we move on to the next slide, and let's talk about the challenges and opportunities here. So EU, of course, as we all know it, EU has a well-established frequency reserve system. However, the renewable energy dominance now, as Shaheen mentioned, causing a lot of fluctuations, and it decreases the viability on the frequency reserve as much as the frequency grid itself, the grid itself. We have most recently observed this in Spain and Portugal, where a couple of things went wrong at the same time. One of them is being fluctuations caused by the renewable energy power plants, and another is a peak demand on a random time that caused a lot of transformers to shut down the operation to prevent any problems in the grid, any problems in the home appliances or the critical infrastructure. So this was one of the bigger problems in the problem that happened in Spain and Portugal, and we're trying to also find a solution for this challenge as well. And transition into renewable energy will require more baseload providers for balancing. And since geothermal energy is a baseload energy, it can be considered as a replacement. However, it cannot be a directly replacement for the hydroelectric or maybe fossil fuel powered geothermal power, fossil fuel powered thermal power plants, because geothermal energy has an always on system. So what does always on mean? In geothermal energy, you cannot simply turn off a production well or a reinjection well for that case. You get the heat from. This might cause reduced efficiency from the well or no flow at all, which will cause a lot of problems since it is one of the biggest capital expenditure. This cannot be risked for the geothermal operations. So this is one of the problems that we are going to overcome, or at least try and overcome in this project as well. The next one on our agenda is EU has mostly low enthalpy geothermal, which fits ORC or district heating cooling options. We mentioned this a couple of times before during our presentation, as also Shaheen has mentioned this. Due to sedimentary formation, there is less heat that can go up. There's less fault lines. There's less flow coming up from the core to the crust to the reservoir, and from reservoir to the surface. And also ORC efficiency changes drastically over the year due to ambient temperature conditions. In ORC systems, since there is really not so much, sorry. In ORC systems, since water is not really abundant compared to the flash or dry steam power plants, air-cooled condensers are utilized. ACCs highly rely on the ambient temperature conditions. During summer months, with increased temperatures, the condenser temperature pressure increases, which causes drastic decreases in power generation from the ORC power plants. It's almost up to 55% in some cases. So these are the challenges and opportunities that we have at our hand, that we can utilize geothermal as maybe a future replacement of the existing power plants. So this is where the Angel project comes in. As the name suggests, and the project suggests, main goal is to create the tri-generation from a geothermal, which is providing heating, cooling, as well as power generation, which is the main operation at the geothermal power plants. This will be achieved by joining a couple of innovations, a couple of state-of-the-art technology with the innovations we have to add flexibility as a prospect to geothermal power plants, while being able to provide power, heating, and cooling on demand. Additionally, a separate cooling method will be applied to existing ORC plants, and this cooling method is absorption chillers. Absorption chiller will be utilized to help cooling process in the ORC plants with different configurations. We will try out before and after the ACC systems, and we will also add a recuperator to test out the system, which I will talk about in the demonstration cases. The system will work, of course, aligned with the heating grid supply and demand conditions with help of the storm controller, which is developed by one of our partners in the project, Vito. The storm control will be implemented into the energy management system that's created solely for the project with the help of the naldeo team, another partner in the project. Storm will analyze data from previous years, weather forecasts, and will create a decision support system, which will feed its data to EMS, making the system smart, efficient, and flexible. Now, if we move on to the next slide, I'm going to have to just do it manually again. There we go. So let's talk about our work packages. I think since most of our guests here have already had some experience about the Horizon Europe projects, so this is a quite generic structure for the work packages, but let me just explain how they work. In work package 1, we have already established the main ground for the requirements of the system, and main equipment specifications were created. Work package 2 focuses on the thermal energy storage solutions, both cold and hot, which will be utilized in our systems for storage purposes. In work package 3, as the name suggests, it focuses on the control strategy and the management of the nGEL system that we will be demonstrating in Kızılderili 2 geothermal power plant. In work package 4, all our partners will contribute, but we, as Zorlu Energy, will be in charge of the operation. We will try to demonstrate and validate that what we created in theory can actually be achieved in real environment, and can be a flashlight into the future for the investors looking for investments in the geothermal area. In work package 5, I think there's a small typo there. The work package you see on the bottom is work package 5, not 6. And in work package 5, we will focus on the sustainability and try to create awareness around the project and its ideas. All the work done from work package 1 to 5, and of course to 6 to 7, will be done under the supervision of the work package 6 and work package 7, which are the communication and the coordination work packages in our project. So let's now jump into how our demonstrations work and what we will try to demonstrate. I'll try to keep it as simple as it is, but it's a quite complicated project, so please bear with me on this one. I will try to answer all your questions after the presentation as well. So as you can see, the initial concept of the design is as you can see on the flow diagram on the left. We will utilize two thermal energy storage systems for flexibility. One of them will be on the hot side, and one of them will be on the cold side. On the cold side, we will generate some cold heat or cooling with the help of the absorption chiller. And if the demand is not high or there is no demand for the cooling at that time, we will store it in the CTES that will be developed by our partners again in the project, Fraunhofer ISE. We will utilize phase change materials for both TES and CTES and store the energy within. Another innovation that we will have in the project is to utilize the TES. And if the demand on the power generation is low, then we will direct the, actually, I think you can see my laser pointer here. And we from the production wells in the concept, from production wells, if the demand is low on the power generation, we will direct some of this flow to the storage purpose, to the thermal energy storage tank for storage purposes. And when the demand stabilizes on the grid, we will start the normal operation and the thermal energy will be stored inside the TES. And if the demand on the grid increases over time, then we will direct some of this stored energy into secondary ORC to generate more power and maybe even be an actor in the frequency reserve market. And we will test out our response time, response duration, and generated power to understand in which market geothermal energy can play a role in. And this will be a huge step for geothermal energy since it has not been used in the frequency reserve market so far, even in the recent years. And the last innovation we have, which I already talked about, is the absorption chiller, where we will provide cooling to the grid if there's a demand. There is also an existing district heating option. If there is no cooling demand or there is no higher demand on power generation, that means if the demand gets lower, then we can provide a direct some of our flow to the grid heating to provide provide heat to greenhouses or to households. Now, moving on to our next slide, which has a more detailed explanation on the screen. I'm hoping this is all visible to you. We want to be able to flexibly provide heating and cooling and power generation. This will be achieved by utilization of the heat source, which in this case is the separator outlet from the power plant. I believe you might remember I talked about the combined systems in the beginning of the meeting. Our power plant, which is Caldera 2 geothermal power plant, is a triple flash combined binary cycle, which means that we utilize the geothermal brine itself directly by generating some steam, and then utilizing the waste heat from the power plant for binary, which is the ORC plant. Then we have the most efficiency from the geothermal brine. In this case, in this demonstration, we will utilize the geothermal brine from the high pressure separator to intermediate pressure separator, which has a lot of energy inside, and act and remove or disconnect the nGEL system from existing power plant to reduce the disturbances in the geothermal power plant itself. So we have a secondary ORC, and our ORC here, which is our partners REPG Energy's design, will utilize this energy for generating some more power in a flexible manner. You can see we have a heat exchanger here. The main purpose of utilizing a heat exchanger is to provide clean water to delicate equipment in the system. So normally geothermal brine has a lot of residue, as we talked about in the beginning, has a lot of minerals that becomes a sedimentation. And if this occurs in the smaller bore pipes inside the system, such as the heat exchanger of the thermal energy storage or the absorption cooler, that means we will have to stop the operation, clean up the whole system, and start again, which will cause a lot of intermittency in our operation. Since we don't want that, we will utilize a clean water loop inside the system. You can see with the blue and purple lines, and we will receive the geothermal hot brine from the high pressure separator, and we will utilize the heat, transfer the heat to the clean water, and then utilize this clean water as the heat transfer agent in our system for all equipment. Only for district heating, which is the HX2, you can see here on the right side. This heat exchanger is a plated type, so it's easier to clean and easier to maintain. So we will be directly connecting this to the geothermal brine. For the rest of the operation, we will be using a cleaner option. So how will the system work? Our control system will dictate how the system will work. If there's a heating demand, then the EMS will run its operation and direct the flow with the control valves to the grid district heat exchanger. If there is a demand on the cooling side, our EMS will order the system to run its control valves to direct the flow to the heat, to the absorption chiller, and if required, to the cold thermal energy storage system. If there is a higher demand on the power generation, the stored energy in previous action, the stored energy inside the TES will be released into the ORC system. This will be accomplished by a series of pump configurations. As you can see, we have a pump here that will be circulating the liquid throughout the system with or without the connection to the heat exchanger and geothermal brine. If there is a stored energy inside the thermal energy storage unit, our pump will run its course. As you can see here, if you can follow my laser pointer, it will go through the thermal energy storage unit, go through the evaporator and preheater, sometimes through the ORC system, and then come back to the starting place, and thus will release the energy inside the thermal energy storage system into the ORC plant. It will add generated power to the existing power plant operations and will increase the overall installed capacity for 3-4 hours. That's our main goal for the flexibility on the power generation side. And similar to the power generation and thermal energy storage unit, if there's a demand on the cooling side, then our loop will only work from the heat exchanger to the bypassing the thermal energy storage system to the absorption chiller generators, thus generating some cooling for the warehouse buildings in this case, because this will be a pilot scale operation, and we have established how much cooling our plant command rooms require, and we will be providing cooling to those buildings. And storm control will play a huge role on this prospect. Since we do not know how much heating will be required to the grid, we will utilize a lot of data from previous years for both greenhouse and district heating options. And this will dictate our system on when, during nighttime, during daytime, when the demand is high, when it's peaked, when it's the lowest, the storm control will provide some ideas to EMS to decide which innovation, which state-of-the-art equipment that we can provide the heating to or cooling to. So let's move on to our second demonstration case, which is on the ORC side. As you might remember, I'm gonna have to use scan. All right, great. So figure on the left shows the ORC module that will be utilized in our nGEL project as the demonstration case too. This will take a longer duration, about 12 months. At least that's the target right now. And thanks to our RPG, they were flexible enough to provide us with different solutions, different aspects of the configuration of the ORC module they have. So in this one, on average, as I mentioned before, there is about 55% drop on the power generation during high ambient conditions. In nGEL project, we are planning to decrease the inefficiency by some innovative solutions. Normally, only ACC is used for cooling purposes. In this project, we are planning to utilize a secondary cooling, which will be supplied by absorption chiller during the high ambient temperature conditions. Additionally, as you can see on the middle, not sure if you can see my laser pointer here, but there's a recuperator here. A recuperator will be used to cool down the fluid on the turbine outlet while preheating the same fluid on the preheater inlets. So that will be increasing the efficiency. By doing so, we are targeting to recover 1 megawatt thermal energy per 1 megawatt ORC capacity, installed capacity. We believe this will increase the generated power 5 to 10% under the mentioned higher ambient conditions. We have a large number of variations that we will need to carefully apply to the system during the project execution phase. First and most important in our agenda, on our list, is to not disturb the existing ongoing activities on the plant, and of course, to not risk any employees' health and safety. We will try each option and analyze the results for the best possible configuration. And as you can see on the bottom right side, the absorption chiller is after the ACC. But of course, we will also try to implement a secondary piping to try out how it would work if the connection was before the ACC, and reduce the ACC load as much as possible, since it's one of the most parasitic loads on the ORC power plants. And if we have already stored some energy, some cooling in the CTES, which is cooling thermal energy storage, instead of utilizing the absorption chiller, we will direct the flow from the CTES to the system to provide additional cooling and reduce the parasitic loads even further by not even utilizing the absorption chiller, which also has a low load that has a burden to the system. So I believe this will be the last slide of my section, but this is again a lot to take in. So I expect your questions at the end of the meeting after Shahin's comments. Thank you.
So thank you a lot, Turan. Really appreciate the nice presentation. And I would be giving like one or two closing remarks as what would be the expected outcomes after all of the project duration and the efforts that we would be doing, and basically what we want to achieve as a general expected outcomes. And the non-technical one would be to basically have cost efficiency. So our aim is to reduce capital and operational and also maintenance costs, and making geothermal energy more competitive in the market. The second aspect of our expected outcomes would be environmental and social benefits. We want to lower the CO2 emissions and have significant contribution to the EU's climate neutrality goals. That's our second expected outcome. The third one would be more related to the technical aspects. That would be the increased ORC competitiveness. So by enhancing geothermal ORC technology's role in Europe's renewable energy landscape, we want to increase the ORC competitiveness. And lastly, we want to provide a reliable renewable energy source to stabilize the grid, as it has been discussed before by Tugrul and myself, especially during intermittent renewable peaks. We want to bring security and resilience to the energy grid. So that's the four main expected outcomes out of the project. And we want to also have an impact on EU policy and economy, apart from the technical aspects. And the first one being policy influence. Within the nGEL project, nGEL aims to shape future of the geothermal energy regulations and smart grid policies. So what we are trying to do is to demonstrate these technologies and innovations and influence the policy in regards to the future of geothermal energy regulations, which is very important and shows the importance of that. Regarding the methodologies, we want to have the potential, we have the potential to create jobs and lower energy costs, especially in the pilot regions. So this is like our philosophy, to create this potential and lower the energy costs, which is like one of the hurdles right now in the geothermal energy sector. And lastly, another impact would be we want to support local energy autonomy by diversifying renewable energy sources. So solar and wind having the dominant share, if I'm not mistaken, at the same time, and geothermal energy not being as impactful. So with our tools developed within nGEL, we want to basically support the geothermal energy as a renewable energy source, basically reducing the dependency on imports and having becoming independent from other energy sources. And with this, I want to wrap up the presentation and thank all of the audience and also Tugru for the nice presentation and you accompanying us. And one other thing would be like, we would be great to be connected with you guys. So my recommendation would be to take out your phone and get connected with us. You see basically 5 QR codes on the screen. The first one is our website. If you want to get information, or if you want to, it would be great actually, please do so to sign up for our newsletter. You can do that through our website. We are active on all social media platforms, specifically LinkedIn. It would be the second from the left side. Scan the QR code, join us. We will be regularly updating all the social media and the websites. So get connected with us. So we will be having new webinars and new detailed information and talks and synergies with other projects. So a lot more is basically planned and will be presented soon. So get connected with us, and thank you a lot for listening. So I would be thankful as the last remark, closing the presentation. Please send your questions. We would be more than happy to answer some of your questions and having a little bit of discussions right now. So I already have, like, from Nekati Akaturk, 2 questions. What kind of synergy does this project offer to each current participant, such as knowledge transfer into their own products or joint product development beyond funding?
Maybe I should take the lead on this one.
Yes.
So thank you, Nejati Bey, for your question. Well, the synergy this project offers is that, as you can see, there is so many different actors from the geothermal sector inside this project. So we are planning to combine those generated knowledge of thousands, maybe hundreds of years of experience in combined uh, experience to create a last product, which will be the nGEL itself, the trigeneration system. And each and every compound in the system is quite important for us, such as smaller collaborations inside the system as well. For example, the absorption chiller combined with the REPG ORC module will create a new and more efficient system for smaller power requirements in distant areas, for example. If you can have a heat exchange rate in between like 20 to 25 Celsius degrees differential temperature in the inlet and the outlet of the system, and combine it with an absorption chiller, that means now you have a fully operational system. You can generate power for a small building or maybe a small house, maybe a larger household. And this is one of the things that this project can offer beyond funding. Also, if we consider the other actors in this sector that is not included in the power in this project, such as the phase change material producers, there's a huge demand on the thermal energy storage purposes right now, and phase change material has a lot of promising prospects to cater for these needs, and this will, I believe, also increase the importance of the products with the units we have in this project. I hope this answers your questions.
Thanks a lot, Turul. There is another question, and while I was reading that, I thought I maybe could be answering that. There are already existing systems from REPG. Is it open? Who can sell the products so that everyone benefits from the shared know-how? So an answer to this question is like, yes, but considering the fact that the project is a research and innovation project at the current state, what we are trying to do is to demonstrate the possibilities and the technology, and also bring recommendations and the know-how to everyone within Europe. So that's the goal of the project. And as the next step, after finalizing the project and successfully demonstrating the technologies, yes, of course, then that's one of the main goals of the project, to share the know-how that will be done, and also looking ahead to commercialization. So that's a big yes, but that would be dependent on moving forward a little bit with the developments and also conduction of the project. And as the project goes on, when it comes to exploitation and also next steps, of course, every step we will be sharing our results, the know-how, and also possible future collaborations and commercializations for everyone to benefit from the developments. So that would be basically my answer to the question. It's a big yes.
Adding to Shine's maybe response, I have to add, I had the opportunity to work with some of the REPG engineers, and they already have a lot of new ideas to add to the system of how we can make it work more efficiently. But they have the ability to adapt to our requirements as a project as well. So of course there will be a lot of different ideas generated from this project, and a lot of information will be accumulated, and this will, I believe, reflect into the future of each and every partner of this project.
Thank you, Toro. Just not to waste any more time, I want to use the time to have you here. Another question from Mr. Osman Kale would be, how do you plan to integrate the concept with conventional ORC plant? Stakeholders believe that sharing any waste heat will negative impact input and reinjection parameters, thus the efficiency of the main plant.
I see. I believe this question is about the reinjection temperature. If we are going to utilize even more heat from the ORC from the geothermal brine, it might cause some problems. So consider the operation as not as a continuation of the existing flash geothermal power plant, but an ORC power plant. In the slides, maybe Shine, if you could just go back a few slides.
Of course.
The initial concept idea of the system. One before, yes, exactly. No, next one.
It's
Yes,
lagging,
I know
so I
there's a
click
delay.
and then it just goes.
So as you can see, this is basically an ORC plant. It's a conventional ORC plant that is retrofitted by our ideas. Normally, you can see on the left. Maybe I can just ask for the controller.
Yes, you have.
Yeah, on the left side, you see the production well, its operation, and then the injection well is already an existing system. You have a production well, you have the geothermal brine that you utilize it for evaporator and preheater, and you reinject it. There is no additional heat load that's been removed from the geothermal brine. Thus, there is no decreased temperature on the geothermal brine. If we retrofit the nGEL ideas into the system, if we retrofit the nGEL ideas into the system, that means still there is no additional load taken from the geothermal brine, but now it's used instead. So if the demand on the power generation is decreased, that means you need less load on the evaporator and preheater. That means now you have additional power, additional heat that you have that you will normally just waste, but in this case you can use this waste heat to generate some more cooling, heating, or store this energy for further use in a secondary ORC. That's the main goal here. So this can be easily retrofitted to the existing power plants, existing ORC power plants. Only in our case, we are using the main heat load from the power plant itself because we think for the auxiliary 2 geothermal power plant use case, this is the best option. But in normal operation with the traditional conventional ORC power plants, this will not have an effect on the reinjection temperature at all.
And thank you a lot, Ulrol. Just maybe it was a lack of providing information, because this is a very great question in the project overview. So the whole idea of the nGEL project is to bring flexibility to the existing ORC power plants. So it's not for the power plants that are being built up. It can be implemented, but at the same time, it's all about the idea of bringing the flexibility by the additional technologies to make it a tri-generational power plant when we have an existing ORC power plant or when one is in development. Just as a complement, just like for the overview, these are the two goals, and it doesn't go against the idea of existing ORC power plants not being able to be used for these purposes. We are running out of time. Turul, I have one more question from Mr. Jakaria Mahmoud. What kind of material or equipment will be used in the nGEL project? Will any rare earth material be involved?
May I?
Yes, please.
Yeah, thank you. So in this one, I believe the most complex thing we're going to be using is the phase change materials. The rest of the items, the rest of the equipment and the materials are quite standard for usage. For example, we will use carbon steel and stainless steel where it's needed. When if there is corrosion, we'll go for the stainless steel. may it be duplex or super duplex, and we will use carbon steel where there's just normal flowing water, such as the closed loops I just mentioned in the beginning of the project. Maybe if I have still, yeah, I have the control still. Yes. So in the clean water loops, we'll probably use carbon steel since there will be less corrosion. But in the if there's any instrument air, for example, that's going to be used, which will be used, of course, with the EMS, then we'll use stainless steel. The only complex material we will use in the project is the phase change materials. And in this one, we have chosen HDPE for the hot section, which is high density polyethylene, which is not really a rare earth material. And the second one we chose for the cooling part, we are still in the process of selection of material, but the one that comes up looks to be paraffin, which is again is not a rare earth material. So in this project, we will basically use the existing state-of-the-art equipment and the innovations, but we will use them in a manner that is so very well compiled together. We believe this is the innovation itself. We will be adding the flexibility aspect without adding any damage to the environment itself.
Thank you, Alan.
I'm hoping that answers your question.
I believe it was for me at least. So I think we can do one more, and I would be taking over that from Mrs. Shurubi from the audience. Have you gathered and analyzed the real world data on dynamic power, heating, and cooling demands and the methodologies? So basically, this one I can take over because it would be rather more on the data side. So basically, a big yes to the question. So the whole idea behind the technologies is also have this energy management system and also the control system that is AI and data driven. So one major effort that is happening in parallel to all the technical development that mainly Tugru was also presenting right now is to have an AI driven or data driven AI based models that would be doing the energy management system to make the flexibility in the trigeneration happen. And that basically is dependent on having enough data. So we are in talks. Also, Zolu Energy and Toru are in talks to acquire as much data as possible. Partly the data are available. Basically, the data sets are available publicly, and whenever it's not available, very nicely, we hear from a lot of energy providers that they are willing to provide the data. So the combination and collection and pre-processing of the data would be the backbone to the energy management system that will be basically supporting all the developments that you see on the screen and has been presented in the last minutes. So I hope that more or less is sufficing. And when I look at the time, it's almost 7 minutes past the 3. So I would like to finish the webinar right now. I want to thank you all again for joining. And once again, I want to invite you to scan the QR codes and join us in our social media and the website to get connected and have more events, the upcoming events, so we can get connected. And once again, thank you, Tugrul, and the audience for presenting and respectively listening to us and spending your time.
And thank you everyone for listening, of course, again. And hopefully we will share the results of the project as well during the project period. We will be having a lot of webinars such as this one, and we'll be happy to share the results with you as well.
Okay. Thank you, everyone, and I wish you a lovely weekend ahead.